Hello everyone. Uh, so this is a new video on this video is specially about interview preparation, how questions are asked in PhD interviews, whether it is a PhD interview or your lectureship interview or any interview related to physics. This video will help you. Okay. So basically, you will be asked in PhD interview tell us about first you have to introduce yourself and after that what have you what project you have done in your masters and what are your research interests and what are your particular research interests if suppose you tell my research interest is in high energy physics, so what is a particular research interest, whether it is beyond standard model or particle physics phenomenology. Even in that you have to say suppose in neutrino physics or flavor physics or quark physics or like CP violation, um, or dark matter physics, or astroparticle physics. Suppose you say in astrophysics, suppose like yeah, in high energy physics. Suppose in high energy physics, you can say there are so many variations. Like suppose neutrino physics is there, neutrino physics, and then your flavor physics, which kind of deals with quarks, gluons, all those things. Then there is this quark gluon plasma. Okay, so you cannot just say high energy physics because panel is already high energy physics. So you have to say the particular field of interest that you are interested in. It can be quark gluon plasma, or suppose physics beyond standard model. You know, beyond standard model, or like quarkonia, quarkonia production, charmonium, quarkonium. Those things are also there. So these are some of the interests you can go in energy physics. In astrophysics, also you can have radio physics or extragalactic astronomy, extragalactic astronomy, or data-driven astronomy, data analysis of astronomy, and like Earth astronomy, astrophysics, solar astrophysics. You can have also solar astrophysics or nuclear astrophysics. Suppose nuclear astrophysics, then so many things. Then high energy astrophysics, gamma ray bursts. Hmm. So it's like astroparticle physics. So a lot of variations or a lot of fields domains are there. So you have to say particular field. You cannot just say high energy physics, astrophysics, or whatever. Okay. In condensed matter also it goes the same way. So after that, suppose you say neutrino physics. So you'll be asked questions related to high energy physics, like what things you have studied in high energy physics during your masters, and yeah, it will go like that way. And you have to be really thorough with standard model, particle physics, Feynman diagrams, and um, all the particles, spin, isospin, strangeness, then Schrodinger equation. Most important things are Schrodinger equation, then Dirac equation, proper proper description of Dirac equation, what it does, what it doesn't do. Then your Klein-Gordon equation. I was asked Klein-Gordon equation, Dirac equation, in so many places that I went for interview. And what is the difference between Dirac equation? How do you distinguish between Dirac equation and Klein-Gordon equation? Which spin particles obey Dirac equation? Which spin particles obey Klein-Gordon equation? Which has the relativistic, which acts in a relativistic domain only, which acts in both non-relativistic and relativistic. Okay, like Dirac equation acts in a relativistic region, and Dirac equation also gives Dirac equation gives me two values of energy, positive and negative, whereas Klein-Gordon equation has only positive range of values of energy. Okay, Schrodinger equation. Why started Schrodinger equation didn't work? That's why we have to get the Dirac equation, because Schrodinger equation was not Lorentz invariant. That's why like it didn't work relativistically. So for relativistic quantum mechanics, we had to get a Dirac equation, right? So these questions, what are Dirac spinors? Okay, those things will also be asked. So yeah, let's start some questions. Okay, next after this introduction type, you will be asked to tell us two of your favorite subjects or topics in physics, so that I can ask the questions. So I said, so the strongest topic should be told first. You should tell your strongest topic. I said my two favorite topics were electromagnetism and quantum mechanics. Don't touch anything that you are doubtful about. The so these were my, and also the order of it also matters. Okay, if you say quantum mechanics first, they will ask from quantum mechanics. If you say electromagnetism first, they will ask from electromagnetism. So this is the order. The order also matters. Okay. So first, let's go to electromagnetism. Okay, what questions can be asked from electromagnetism in interviews? Okay, so electromagnetism. Let's do next page. Electromagnetism interview questions. It can be a PhD interview or interview for lectureship or any kind of interview related to physics. Okay, interview electromagnetism interview questions. Okay, basically, basic questions will be asked. So I'm not going in any order. I will just tell you the questions that really pop up in my mind. Okay, so that were asked to me in the interviews. So this is kind of a, it's not in order. Okay, it will be just the questions that were asked to me in the interviews. Okay, so first question, this question was asked to me in IIT Dhanbad. So this question, what is pointing vector? Simple, very question, a very easy question. What is what is pointing vector? Okay. So what is pointing vector? Pointing vector is what? What is it? Pointing vector is the vector that represents the energy flux density of an electromagnetic wave. Okay, like the rate of change of energy transmission per unit area, or the directional energy flux of an electromagnetic field. How the energy flux goes in the electromagnetic field, that is the pointing vector. It's used to calculate the power flow in electromagnetic fields. Okay, and also it gives the information about the direction of energy transport or the propagation of electromagnetic wave. All right, so we can write the answer. Don't worry, I will write the answers also. I will not just speak. So, pointing vector is a vector that represents the energy flux density, energy flux density of an electromagnetic field. Okay, energy flux density. Okay, and if we write it mathematically, like qualitatively, we can say it's the rate of energy transmission, rate of energy transmission per unit area. Okay, okay, or we can also say the directional energy flux of an electromagnetic field. Alright. So pointing vector is actually the cross product of electric and magnetic components of the field, we know S vector is equal to E vector cross H vector. Okay, so this is simply your pointing vector. Okay, what is the use of pointing vector? Next question can be, what is the use of point? This is you told the definition. So what is the use of it? What's the use? What is the use of pointing vector? What is the use of pointing vector? What is the use of pointing vector? So pointing vector is used to calculate the power flow. Okay, used to calculate the power flow in electromagnetic fields. Power flow in magnets. And it also gives the information what provides provides information about the direction of energy transport and propagation of the electromagnetic field. Okay, used to calculate the power flow in electromagnetic fields and provides information about the direction of energy transport. Because E cross H is giving me S, so the whole electromagnetic field direction is your pointing vector direction. So it is the also the propagation of energy is also, because the whole wave, if this is your electric field, this is your magnetic field. So this is a magnetic field. Electric field along, suppose Y, magnetic field along Z. So the whole wave is moving along X axis. So the whole wave, that means the whole energy transportation is also along X axis. Alright. So the unit of pointing vector will be what? Unit will be watt per meter square. Okay. It's kind of power by area. Okay. Power by area. Right. So this is your pointing vector. Right. You can also write the formula as to vector is equal to E cross B by mu naught by mu, because H is equal to B by mu, right? So S is equal to E cross B by mu, where mu is the permeability of any medium, right? So it what it does is it helps in calculation of direction of flow of energy. Okay, it also helps in studying how electromagnetic waves interact and propagates with the surroundings. Magnitude of the pointing vector gives us what? Gives us the power density of the electromagnetic wave at any specific point, which also helps us to study field intensity at different points in any surrounding. Okay, yeah. So this is simply a pointing vector, which is a very important question for any kind of interview, any physics interview. Right. Next question. Next question is, as you are asked pointing vector. So next question will be directly, what is pointing theorem? What is pointing theorem? Okay. So what is pointing theorem? So pointing theorem states that the rate of energy transfer per unit volume from a region of space equals what? The rate of work done on the charge distribution in the region plus the energy flux leaving that region. Okay. This is a very good question. Okay, write down the rate of energy transfer per unit volume. Rate of energy transfer per unit volume from a region of space equals The rate of work done. The rate of work done on the charge distribution, on the charge distribution in the region. Okay. Yeah. Plus the energy flux, plus the energy flux leaving that region. Alright. So this is your pointing theorem. Okay. So if I try to write it mathematically, yeah, I try to write mathematically, it will be what? Rate of change of energy transfer per unit volume. That means kind of energy density. Rate of change of energy density. So can I write like this? Is equal to rate of work done. So minus del U by del T is equal to rate of energy density minus del by del T of half epsilon naught E square. We know it plus 1 by 2 mu naught H square. Is it correct? Can this be like this is energy density of an electromagnetic wave, right? This is electric field energy density, magnetic field energy density. So this is the rate of change of energy density. Okay, and this equals actually del dot E cross H. You can prove it. Okay, minus del U by del T is equal to del cross del dot E cross H. Yeah, right. There's a proof also. If you can prove it, that would be really good. How will you prove it? Suppose I ask you to prove it. Okay. Suppose I ask you to prove it. I will just tell you in short. Okay. So del dot E cross B. Okay. So del dot E cross B. Del dot like divergence of A cross B. You have to remember the formula for it. So the formula is B divergence curl E minus E divergence. Sorry, what I'm saying divergence dot. Sorry, B dot call of E minus E dot call of B. Yeah, we know this one is what? This is your third law, Maxwell's third law or Faraday's law. So B dot minus del B by del T minus E dot. What is this one? This is the fourth law, Maxwell's fourth equation, modified Maxwell equation, and I can add mu naught epsilon naught del E by del T. Correct, leaving the other term. Okay, so this can be written as B del B by del T minus E dot, okay, mu naught epsilon naught E dot del E by del T. Correct. After that, after this, you have to do a bit of algebra, and finally you will get it. Okay, you will get this one. All right. Okay. So this is your pointing theorem. Okay. This is what? This is your pointing theorem. Again, a very important theorem, pointing theorem. What it says, conservation of, like it refers to conservation of energy for electromagnetic, okay, where the total dissipated energy flow through a closed surface in the field is equal to rate of change of complete electromagnetic energy inside a bounded volume. So rate of change of energy in a bound volume, that means energy density, is equal to rate of change of dissipated energy flow. Dissipated, that means that's where there is negatives. All right. Okay. So this is your pointing vector, pointing theorem, pointing vector. What other questions can be asked from this part, or were asked to me? Okay. Next question that was asked to me was, what is displacement current? Okay. What is question number three? What is displacement current? So displacement current was given by Maxwell, and it was added in the Maxwell's fourth equation, if you remember. Yeah, del cross B is equal to what? Or del cross H is equal to epsilon naught del phi by del T plus J dot ds or del dot J. Okay, so this is your normal like conduction current. This is your displacement current. Del cross H is equal to displacement current plus conduction current. Okay, so that was what it was. So how why this displacement current term was introduced? First, the formula was like this: del cross H is equal to del dot J. That means what it was, or you can say it was like this: mu naught del cross B is equal to mu naught epsilon naught what del rho by del T, right? So something like this, right? Yeah. And B by mu naught become H. So epsilon naught del rho by del T. Yeah. So del rho by del T becomes del dot J. I think. Yeah. I think that yes. So that term was given. If we take the divergence of both the sides, it would have given us zero. So, but zero is not possible for del dot J. Del dot J is not zero. That's why there was another term was introduced, which upon adding with conduction current will give the whole thing as zero. That's why the displacement current was introduced. Okay, so displacement current formula is what? ID is equal to ID is equal to ID is equal to epsilon naught del phi by del T. What is displacement current? How it is different from the normal conduction current? Displacement current occurs due to the change in electric field between the plates of a parallel plate capacitor. Okay, change rate of change of electric flux. Okay, between the capacitor plates. All right. The usual current comes because of change in magnetic field. Because of change in magnetic field, there is magnetic flux, and because of magnetic flux, there is a current. But here, um, this displacement current is saying that it can also occur because of rate of change of electric field, okay, or electric flux through parallel plates. Yeah. So we can say what displacement current is, what rate of change of an electric displacement field or electric displacement field, which is your D, okay, over time. It's a time varying electric field. This one is a time varying, so time varying electric field and not an electric current. It's not caused by, it's not the electric current produced by moving charges. It's not produced by moving charges. Instead, it's produced by change in electric field. Okay, it's important for understanding electromagnetic waves. Okay, and it's very essential for the continuity of magnetic field between the plates of a charging capacitor. It's also responsible for causing capacitor current to lead voltage, which increases the power factor. Okay, so it's a very important term, displacement current. So this thing becomes the like the Ampere's law was only conduction current. So now the whole thing is the conduction current and displacement current gives the whole current, the total current. Okay. Yeah. So how it occurs? There is like the charge within an enclosed surface is changing. So it is necessary to add another term in the Ampere's displacement, Ampere's Sauter law. Okay. Yeah. So this is your displacement current. What like unit it has? It has the unit of electric what displacement current. Okay, displacement current. Or we said displacement current density. Sorry, current density. Simply current density or J. Okay, so it will have the unit of J. Right. So this was your displacement current. Yeah. You can be also asked to explain all the equations of Maxwell. All the four equations of Maxwell. Write them in integral form and differential form. Right. So suppose you are asked. So first equation is what del dot E is equal to rho by epsilon. Yeah. We can also write it as del dot T is equal to rho. Correct. So this is the differential form. What if we write it in integral form? So how can we write it? Suppose if I take it over a volume dV, and this is also rho dV. Okay, so do this in the interview. Okay, take all the three integrals. If because I gave only this, and they asked me, is this the volume integral? Because it's a triple integral. So a lot of they go into a lot of detail. So del dot d dV can be written as d dot ds, isn't it? This is a double integral. Is equal to this becomes what? What is rho dV? Is simply charge enclosed. All right. So this is a what? This is your what would I say? The integral form of Maxwell's first equation, which is actually the Gauss law of electrostatics. Okay. Second equation is del dot B is equal to zero. That means what? If we again take the, if I can write this del dot B dV, I will take the volume integral on both sides. Suppose so 0 dV doesn't matter this side. So I can write it as B dot ds. Okay. So divergence theorem, Gauss divergence theorem again here. Gauss divergence theorem was used. So this gives us also zero. So this is the integral form of Gauss law of magnetism or Maxwell's second law, which means suppose this is a surface or volume. Inside this volume, suppose I take a magnet. So the magnetic field enclosed within the magnet is zero over the surface. That means magnetic field always remain in pair. It cannot be a monopole. If it was a monopole, then it could have given me a positive value or any value that is non-zero. Okay, but it is not. That is not the case. That's why it always remains in pair. Okay. So, suppose if I take an electric dipole minus q plus q over the surface, so the electric field over this surface will be what? Zero. Exactly like that. This is the case. Okay, so this is for a dipole, electric dipole. So this is for a magnetic dipole, which is the case. Magnet always remains in a dipole. Okay, so this is the differential integral form. Again, third equation is a what? Third equation is a Faraday's law. Third equation is a Faraday's law of electromagnetic induction, right? And also the Maxwell's third equation, which is del cross E. Call of E is equal to minus rate of change of magnetic field. Rate of change of magnetic field gives rise to electric field, and rate of change and also electric field gives rise to magnetic field. So electric field and magnetic field are interrelated. They are not separate events. Okay, one rate of change of one thing will give rise to rate of change of gives rise to the production of the other. That was given by Faraday. Okay, so they are not, they are single phenomena. They are like interrelated. So if I write again, I will take the divergence on both sides. Divergence of del cross E. Oh, sorry. Okay, let's do one thing. Del cross E ds surface integration is equal to minus goes out, integration surface integration del b by del t dot ds. Okay, over any other surface. So this will give me what, E dot dl. This is Stokes theorem. Okay, this is your Stokes theorem. This is a closed loop, and this will be giving me when minus. Okay, it will come out. It will become d by dt. Okay, complete derivative. So this is your, no. This is not closed surface. Sorry, if it was closed surface, it would have given me zero. Closed surface integration of magnetic field is zero, isn't it? So again, have to be very careful. So b dot ts. So this is the what? This is the so this is exactly flux, isn't it? Electric flux. So electric flux is equal to this is again, okay. This is why electric field dot dl, which is equal to what, EMF, isn't it? This is EMF. We know this is EMF, correct? Okay. So yeah, this is your integral form of Maxwell's third equation, or your Faraday's law of electromagnetic induction. Okay, and your fourth, this is the Stokes theorem was applied, direct Stokes theorem applied. Okay, the fourth equation is a what, del cross H is equal to what, J plus del D by del T. Is that correct? Del cross is equal to J plus del D by del T. So if I again del cross H ds surface integration, surface integration is equal to JDS plus again in the surface integration del D by del T ds. So this gives me H dot dl becomes line integration is equal to J dot ds is J dot ds is your conduction current, right? So conduction current, and this is as usual d by dt of d dot ds. Okay, and this is what, this is actually your displacement current, isn't it? So this is the beauty of the Maxwell equations. S dot dl is equal to IC plus ID. Or you can stop here also, no problem. So this is the integral form of Maxwell's fourth equation. This is actually modified Ampere's law. Okay. From here only displacement current comes. Is that correct? Okay. Yeah. Very good. Yeah. You can ask. You can be asked. What is electromagnetic induction? Okay. Rate of change of electric magnetic flux through any closed surface will give rise to EMF in the circuit. Okay, and that EMF will give me current. So these are also very important questions. You can be asked Lenz's law, Faraday's law, all those basic things. Okay. Okay. So These are some of the questions that may be asked in the interviews. Okay, we'll do more videos on interview preparation. Okay, these will be very short, brief videos. I don't want to bore you too much because sometimes it becomes too heavy and it doesn't go inside your mind. So we'll do three, four questions in every video, and that will really help you. Okay. Okay. Thank you very much.